This is a difficult script for me to write, and I would imagine it's going to be a difficult video to make. The incident I'm going to cover in this video, the Florida International University bridge collapse, caused people to die, and that is genuinely horrible. I am not able to do justice to that level of emotion in this video. The incident in question was caused by engineers doing bad maths. I'm an engineer. I understand the position of those who made the bad decisions and which directly led to this horrible incident. I can sympathise with both sides of the equation. It is losses all round, no doubt about that. I want to tell you that engineering is a burden, that designing big important things is a heavy load to carry. I could try and engender a certain amount of sympathy for the plight of engineers in general. Heck, I set out on this process of discovery with a completely open mind. But the engineers who designed this bridge, they done f***ed up real bad. Now, there is one very particular f*** up which directly caused the collapse, and because it is the big f*** up, I have a lot of information about how and why that occurred. And it is important, but there are other engineering aspects about this bridge that are troubling to me. You are probably looking at the runtime for this video and wondering how I could stretch one big f*** up over this length of time, and the reason is simple. We aren't just discussing one big f*** up, we are going to be discussing several, some of which ultimately played a direct role in the collapse, and some of which merely indicate to me the flawed thinking that went into the design of this fateful bridge. There is a lot to cover. Let's start at the beginning. A bridge was required to link the town of Sweetwater with the campus of Florida International University. A design brief was prepared. Engineers and contractors were appointed. It began construction. March 15th, 2018, approximately 1:46 in the afternoon, before it had been finished, the bridge collapsed. This is how an engineer tells a story, by the way. I'm not wasting valuable video time on storytelling when there is some serious engineering to get into. The bridge is unusual in a number of respects. For a start, it is concrete, and concrete is heavy, really heavy. For a pedestrian bridge carrying relatively modest loads, constructing it out of concrete is very unusual. Steel would have been a much more logical choice. Now, this might seem like an obvious problem. Concrete is heavy, we get it. So just design the damn bridge for that extra weight, right? Well, yes, but also no. The first thing we do when designing structures is to produce a loading sheet. This will detail all the main components of the structure we're about to design and all of their various weights. It serves as a quick reference sheet so that we don't constantly need to calculate the same thing over and over again. It also serves as proof, as something that a senior engineer can check to make sure our designs are founded on solid principles. It's literally the first thing we do. If we get it wrong, then everything that follows is wrong as well. For a concrete structure, where probably 75% of the structural strength of the material is being used just to support its own weight, because it's so damn heavy, the dimensions of the final piece of concrete serve two effects. If we have a slab and we make it thicker, yes, it gets heavier, but it also gets stronger. Let's say we set out a loading sheet for a concrete slab. It has a certain thickness, so it has a certain strength and weight. When we run our calculations, we find that the slab isn't strong enough. We need a thicker one. But by making the slab thicker, we make it heavier. So it still might not be able to do the job we need it to. It needs to be thicker again, but that makes it heavier. Do you see the issue? I am exaggerating this effect hugely here to make my point. In reality, if we end up even remotely close to this kind of circular engineering logic, then something has gone very wrong, and whatever it is we are designing needs a complete rethink. But this doom loop effect has small consequences of a sunk cost fallacy type nature. I need to design a concrete bridge, but before I can design it, I need to know how heavy it is, but I don't yet know how strong it needs to be. So when it comes to concrete thicknesses, I guess. I design the whole bridge based on these guesses, analyse the forces, work out how strong each element needs to be, work out all of the sizes of all the individual members, and then once that is done, I have to do it all again. I have final sizes now, so I also have final weights, which are probably quite different to the original weights I guesstimated. So now I just need to do a final design with all of these updated weights and bingo, all good, right? Well, no. What if the changes in weights affect the strengths required again, and now I need to do it all again? And this is before we consider the effect of load combinations. When we design a structure, we have to design it for every eventuality. And there isn't just one eventuality, there could be dozens. Wind blowing from different directions, varying patterns of pedestrians, earthquakes. What happens if the wind blows from here and we have this distribution of load on the bridge and an earthquake happens all at the same time? What if the wind blows from here instead? What if it's a different pattern of pedestrians? What if it's a different earthquake? All of these events have individual possibilities, how likely they are to happen in isolation, as well as combined possibilities, how likely they are to happen together. When we analyse a structure, we aren't just designing it for one thing. We are designing it for potentially dozens of things that could also interact. Running these kinds of designs for potentially dozens of scenarios while also trying to deal with the concrete self-weight doom loop from before, that is a horrible situation. There are simply too many variables. Anyone remember algebra from school and the effect that increasing the number of variables has on general mathematical complexity? Imagine that, but as a building. If it were me, I would want to fix the structural sizes and therefore the final weights of the structure as soon as possible, if for no other reason than to reduce that number of variables. I would want to make a final model with final sizes that I could just run load tests on. But by making a final model, I am also limiting myself for the future. What if, after fixing the structural sizes and spending weeks building a model and investigating different load patterns and scenarios, I find that I need to change structural sizes and therefore the base loading? I could, potentially, be starting right back at the beginning again with another month of work ahead of me. I am simplifying and exaggerating here massively to make my point, but it is not without merit. Reinforced concrete is a labour-intensive thing. Every single bar in it needs to be planned out meticulously in advance. Making small changes to that is a big deal. Making big changes can be a complete hassle. There is a sunk cost fallacy with reinforced concrete that cannot be ignored, even if I'm not really doing the full issue justice. The self-weight of concrete is just one good reason why we don't generally design a high-performance, long-span truss bridge in reinforced concrete. It's why they are generally all made of steel. I would hazard a guess that 90% of engineered steel structures around the world assumed a self-weight for the steelwork at 0. This whole problem I'm talking about with concrete, its self-weight and designs going round in circles, we, as engineers, generally avoid that problem with steel by assuming it weighs the same as air, which makes the analysis so much easier. You have no idea. With concrete, 75% of the challenge is in dealing with its own self-weight. For steel, that problem doesn't exist, or it's so negligible as to be irrelevant. But this is just one reason why concrete was a bad choice. There are others. For a start, for all intents and purposes, concrete does not have a tensile capacity. If we put a piece of concrete in tension, then for our calculations, it would just immediately yield. To get around this problem, we put reinforcement in it, and this allows us to use concrete in ways other than just in compression, like bending. When we bend a thing, the bottom surface goes into tension and the top surface goes into compression. Without reinforcement in the bottom of concrete beams, for sagging moments, I guess I should clarify all this stuff, concrete is not able to bend. It would just immediately yield. So here's the thing. A bridge spans a long way. It will be under very large bending loads, which will result in both very large compression forces and very high tension forces. If you had a blank sheet of paper, would you choose concrete as the material to bear those high tension forces? Why? The only way it can bear those forces is because of the steel reinforcement buried inside it. So why not just remove the concrete component, make it a proper steel element instead, and save an absolute monstrous amount of load? What does concrete bring to the equation other than problems? That's a really good question, Bigfoot, you might be saying to yourself. And the answer, if I'm being completely honest, is that I have absolutely no idea why they did it this way. It makes no sense to me that this is what they would choose to do, to such an extent that I've actually done some research. April 2015, Florida International University won a bridge. They hire a company to produce a design brief which sets out all the performance criteria that the bridge needs to meet. Okay, let me just put it on the screen. This design brief is what competing engineers were trying to achieve. If this were a sport, then this document represents the rules by which the engineers were competing. So the document starts out with an architectural vision. This structure should function as more than just a place for circulation. It should be a place to be and a place to be experienced, usual architectural gumph. We have a bit about bike access and ramps and stairs, datums, design loadings, and then we get to section 5.9, we have this statement. The bridge superstructure should be primarily structural steel with concrete walking surface. The design brief literally says it should be steel. Where did this idea for using concrete actually come from? I still have no idea. I've been through the accident report, this accident report into the bridge collapse, the causes, the sequences of events, and I can't find a single thing that explains why this bridge was constructed with load-bearing, reinforced concrete tensile members. They mention repeatedly that this was unusual, that it wasn't common for bridges to be constructed in this way, but I can't find a single instance of someone asking why. Maybe this is just an engineer asking silly questions, who knows. It will remain an open question that requires answering, but in terms of the video, we need to move on because we have barely started. I could speculate as to why this has happened. From my perspective, this is a little bit off script, but from my perspective, if you imagine a competition and 4 or 5 engineers were competing in that competition and they were all told it was going to be steel, and one of those engineers turned up with a concrete design that clearly didn't satisfy the rules, the logical choice would not be to give that design the job. You're incentivizing people to break the rules, and then 3 or 4 other engineers turned up meeting the rules and you completely ignored them and went with a design that didn't meet the rules. You set out the rules for a reason and then you chose the one that broke them. It all just feels wrong, but I don't know why. I can't give you an answer as to why it happens. This is a cross-section through the bridge. This is not the shape or geometry of the average bridge. This is different, for reasons that are also seemingly unexplainable. This bridge is like an I-beam. We have a bottom flange, a web, and a top flange. Pretty standard stuff, to be honest, for an I-beam, but not for a bridge. Most truss bridges, I'm going to go out on a limb here, all truss bridges have a minimum of 2 trusses to form that bridge, other than this one. 1 truss along either edge, and then the bridge deck links the 2 together. That's the common way. An I-beam is designed to take a vertical bending moment, and pretty much only a vertical bending moment. That is why it is the shape that it is. Big flanges top and bottom to take the large compression and tension forces, and then a web to link the 2 together. The most efficient shape for compression, to give you an example by way of comparison, is a hollow circular tube. The shape and geometry of a structural member plays a very big role in how that member performs under different loads. If you have a different load, then you generally want a different shaped member. And bridges, when it comes down to it, are really just a very big beam. But an I-beam is only really good at doing vertical bending. And if we think about all those load combinations from before, all applying different loads to our structure at different angles, the bridge isn't only doing vertical bending, it has to do a heck of a lot more. This cross-section, the shape and geometry that was chosen for the final bridge design, is not inherently suited to the job it was being asked to do. If, once again, we approached the problem with a blank sheet of paper and started from scratch, this would not be the natural choice. And to illustrate why, I'm going to propose a plausible scenario that the bridge should have been designed for, but because of the inherent shape and geometry that the bridge was, I know it would have been a problem. And the reason I know is because they mention it in the accident report as something the engineers were concerned about. Torsion. Torsion is a really difficult load, structurally speaking. Well, I suppose let me clarify exactly what I mean. I fucking hate it. It is an out of balance load that is difficult to, well, balance, and it has extremely deformative effects on structures, particularly structures which are the wrong shape. So let's take the bridge. The bridge is running over a major highway. I want you to imagine that there is a car accident on the highway below to one side of the bridge. Everyone on that bridge will rush over to the relevant side to see what is going on. This creates a torsional load on the structure. The centre of the bridge is this line, the centre of the group of people and the force they exert is here, times the two together and we have torsion. For I-beam-like structures like this, all of this torsion is being restrained by a single junction. This junction right here. Whatever concrete exists here is having to deal with the entire torsional element of this loading scenario. And let me explain why it is bad. When we try and restrain a thing like this, the dimensions of the thing restraining it are very important, just like everything else. Crucially, the distance between the two most extreme faces of that element. So for this concrete cross section, the dimension we are looking at is this one. Let's take another bridge, a more boxy type one. When we apply a torsion to a bridge like this, then the relevant dimension to compare it with the Florida Bridge is this dimension, the entire width of the bridge. Take a ratio of those dimensions, so divide one by the other, and that will give you a rough ratio of how effective each bridge deals with torsion. What I'm trying to say is that a standard box type bridge would have a torsional resistance 20 times, 30 times, maybe more than the FIU bridge will, the one that collapsed. It is why boxes are so common for bridges and why this one stands out as an anomaly. This part on the I-beam bridge taking all this load, this is a critical point of failure. This is not the part that actually failed, I should definitely point that out. This is just me pointing out the inherent weaknesses that the shape and geometry and material and philosophy and abandonment of design brief in favour of concrete tensile members brings to the table, that before we even get to discussing what happened on the fateful day, the structure was fundamentally flawed in my opinion right from the beginning. But before we get to that day, there is just one more thing we need to discuss, and really it is the most important because it is the thing that actually failed, the thing that broke and led to the bridge collapsing. Post-tensioning. Concrete can't do tension. We can put reinforcement in it, and this will allow us to put a certain amount of tension into a concrete member, but it is limited. It is limited because as we put load into the steel rebar, it will stretch, and as it stretches, the concrete will crack just a little bit. If we put concrete structures into environments where there are heavy variable loads, like a car park or something, those cracks are constantly opening and closing. They will widen. Getting the ratio of steel reinforcement to concrete right is actually incredibly hard. The structure has to move a little because all structures move a little, and if we ignore that fact, then that creates other problems. And we do want a little bit of movement because this effectively activates the steel rebar, but we don't want too much because that can lead to excessive cracking. Post-tensioning solves this problem by applying a compressive force to the entire concrete section. The problem is tension, so if we can put the concrete in compression, then any tension is effectively deducted from that compression, and we are still left with a little bit of compression at the end. The standard tension effects of bending are present, but because they are overwhelmed with compression, they are not dominant. The compression is. Imagine a chair with a wobbly leg. Without anyone sitting in the chair, the leg will wobble whenever we move the chair about. But when we sit in the chair, the compression we apply to the leg makes it more capable of resisting lateral forces. It can take a bit of abuse because it is already overwhelmingly in compression. Post-tensioning is a bit like that, but bigger and for concrete. Those are the benefits of post-tensioning, but there are drawbacks. For a start, it is a highly technical arena. There's structural engineering, then there's bridge engineering, And then there's post-tension reinforced concrete truss bridge engineering in that order of ascending levels of technical skill. There might be a few engineers who can do truss bridges and a few who have experience with post-tension reinforced concrete, but I highly doubt there is much overlap. I don't think there are many who can do both. And the reason why I doubt that is because they mention in the accident report that the bridge was unique in this aspect, that no other bridges existed like it. No engineers had experience of this kind of project, simply because it was the first time it had been tried, and also last, I hope. I'm going to constantly refer to this accident report. It is an excellent resource. The mechanics of post-tensioning are as follows. Buried in the concrete, we now have two different kinds of steel. First, we have the standard reinforcement. Well, maybe not standard. The member will be taking significantly more compression than it would otherwise without the post-tensioning, so there will be more reinforcement. But it's standard in the sense that you probably know what I'm talking about. You have probably heard of rebar. The other type of steel buried in the concrete are the post-tension rods. The post part of the description refers to the moment when the tensioning is to occur, as in post-tension occurs once the concrete has already been cast and has set. The alternative kind would be precast, which would be when tension is applied to the steel bars prior to the concrete being cast. On the end of these post-tension rods is essentially a big nut, and depending on the engineer's instructions, this nut will be tightened to varying degrees at various stages along the project. As the nut is tightened, it will put the post-tension rod into tension and the concrete in the section into compression. The clamps I am displaying on screen are effectively doing the exact same thing. The clamp will produce a compression in the member that it is clamping, but the rod that links the two ends of the clamp together will be in tension. In the example I am showing on screen, I am effectively post-tensioning the top and bottom chords of the bridge. What I want you to imagine is that in all the members that were post-tensioned, there are several giant springs which have been wound up to their absolute maximum, being held in place by just the concrete. I want you to imagine the feeling of ping. You know, the moment when all this stored energy is expelled in a single moment, because that is the situation the bridge existed in when it collapsed. Something went ping, and half a second later, the bridge was no more. And all of this was required solely because it was decided to make this bridge out of concrete when it should have been made out of steel. It's a fudge. The post-tensioning was only required because the bridge was concrete, and it is the post-tensioning that went wrong. A bad decision led to another bad decision, and then another. The way the accident report describes the post-tensioning of the structure makes it feel like there was a plan to it, but that some bad things happened as a result of that plan, which were completely ignored. So they just blindly carried on with the plan. More bad things happened, these were ignored too, and then the bridge collapsed. This is a picture that I've taken from the accident report showing a 3-inch crack in a piece of concrete. This is fucking serious. This is something that if I saw on a job I was working on, I would probably instantly have a heart attack. 3 inches, 75 millimeters, that is not something, in my opinion, that can be patched up. But it isn't just the crack that concerns me. It is also the apparent rotation of the concrete surface. Let me just draw some lines on the screen. These two lines represent what I think was a perfectly flat surface, but because of the engineering failures that caused the crack, this line is no longer straight or flat, and the portion on the right has rotated to a significant degree. This picture was taken 2 days before the bridge collapsed. It did not stop them from their post-tensioning schedule. They continued applying more load to the structure after this crack was discovered. Alright then. Let's have a look through this accident report in a bit more detail and go through the precise sequence of events, because I think we have enough technical background to understand a bit better what it is talking about. You know, only taken me 3,500 words to get the technical briefing done. Ugh. At the start of the report, we have the executive summary, and this is obviously designed to be as concise and coherent as possible without losing the important details. I will read it out in full. It is damning and illuminating. Investigation synopsis. On Thursday, March 15, 2018, about 1:46, a partially constructed pedestrian bridge crossing an 8-lane roadway in the city of Miami in Miami-Dade County, Florida, experienced a catastrophic structural failure in the nodal connection between truss members 11 and 12 and the bridge deck. The 174-foot long bridge span fell about 18.5 feet onto Southwest 8th Street, which consists of 4 through travel lanes and 1 left turn lane in the eastbound direction and 3 through travel lanes in the westbound direction. 2 of the westbound lanes below the north end of the bridge were closed to traffic at the time of the collapse. However, 1 westbound lane and all 5 eastbound lanes were open. The pedestrian bridge was under construction as part of the Florida International University City Prosperity Project. On the day of the collapse, a construction crew was working on retensioning the post-tensioning rods within member 11, connecting the bridge canopy and the deck at the north end. About 1:46 p.m, a video camera on a construction pickup truck travelling east approaching the bridge recorded the collapse sequence. The video showed the blowout of the concrete north of truss member 12 and the truss losing geometric stability. 8 vehicles that were located below the bridge were fully or partially crushed, 7 of which were occupied. 1 bridge worker and 5 vehicle occupants died. 5 bridge workers and 5 other people were injured. Probable cause. The National Transportation Safety Board determines that the probable cause of the Florida International University pedestrian bridge collapse was the load and capacity calculation errors made by FIG Bridge Engineers Incorporated in its design of the main span truss member 11-12 nodal region and connection to the bridge truss. Contributing to the collapse was the inadequate peer review performed by which failed to detect the calculation errors in the bridge design. Further contributing to the collapse was the failure of the FIG engineer of record to identify the significance of the structural cracking observed in this node before the collapse and to obtain an independent peer review of the remedial plan to address the cracking. Contributing to the severity of the collapse outcome was the failure of MCM, FIG, Bolton Perez and Associates Consulting Engineers, Florida International University, and the Florida Department of Transportation to cease bridge work when the structure cracking reached unacceptable levels and to take appropriate action to close Southwest 8th Street as necessary to protect public safety. Safety issues. The investigation of the collapse of the Florida International University pedestrian bridge focused on the performance of the northernmost nodal region, 11-12 node, of the 174-foot long main span. The failure of this nodal region was the triggering event for the bridge collapse. Factors in the collapse included bridge design errors, inadequate peer review of the bridge design, poor engineering judgment and response to the cracking that occurred in the region of the eventual failure, and lack of redundancy in the bridge design. Specifically, the investigation focused on the following safety issue areas. The next 4 points detail the critical failures that the engineers made that led to the collapse. I am reminded of an adage I hear in football, soccer, quite a lot. It isn't the individual errors to worry about. People are only human, and it is inevitable that they will make mistakes. It is the collection of errors that really gets you, when 3 or 4 individual mistakes lead to a complete collapse. It is a useful thing to keep in mind when it comes to engineering. We have safety factors on safety factors on safety factors. An individual error leading to a small miscalculation is probably going to be okay in the end, but the systems need to be in place to pick up the big miscalculations, the fundamental errors, to prevent events like this. There needs to be backups and redundancies. I'll get to this in a bit. Not just in the final eventual structure in terms of extra structural members or making the ones we do have stronger than necessary, but also in the mechanisms and methods that are used to design it in the first place. Multiple engineers doing the same design to cross-check. Comprehensive oversight from senior engineers who have direct experience and knowledge of the situation and who should also be doing their own rough back of the fag packet calculations just to make sure those multiple engineers are on the right track. And for big important projects where reputation and lives are at stake, a thorough independent review by an engineering firm completely unrelated or aligned with anyone else on that project. That is how events like these should be avoided, and the next 4 points directly illustrate this collection of fuck-ups. Bridge design and construction plan errors, section 2.3, and unique bridge characteristics and mechanisms of failure, section 2.4. The uniqueness of designing a concrete truss bridge led to the circumstances that accounted for the collapse of the pedestrian bridge. The bridge design team made two errors that resulted in the underdesign of the nodal area 1112 that failed, resulting in the collapse. First, the design team underestimated their demand, the loads imposed on structural members that would be acting on the nodal area. The investigation compared post-collapse calculations for the demands on the node with the design calculations. The comparison found that the demand for the node was nearly twice what the design team had calculated. The investigative report discusses how this error was made. Second, the design team also overestimated the capacity of the node to resist shear, the horizontal force, where the nodal region 1112 was connected to the bridge deck. This overestimation was the result of the designer using incorrect loads and load factors in its calculations. These two design errors resulted in a node that lacked the capacity to resist the shear force pushing the node to the end of the bridge. The NTSB recommends improving the discussion of calculating demand loads and capacity resistance in bridge design guides. As we work our way through the report, I will go through in detail what all of these things mean. But what this basically says is that the collapse wasn't caused by a single miscalculation, but by a collection of calculation errors that, when combined, essentially meant the bridge was overstressed by a factor of about 2. The bridge was actually taking about double the amount of load than what the engineers thought it was. The obvious inference that I would make here is that, in essence, at the junction that failed, the structural members need to be about double the strength than they actually were, so double the size. That is a monumental f***up. Independent peer review of complex bridge design, section 2.5. Errors in design may occur, but systems should be in place to catch those errors when they do occur. In this case, a firm was hired to independently review the bridge design for errors. However, the review conducted by this firm did not evaluate the nodes of the bridge truss where they connected with the bridge deck and canopy, nor did it consider the multiple stages the bridge construction involved. Although the design reviewer recognised that he should have examined the nodes and stages, he indicated that there was not enough budget or time to evaluate those factors. Contributing to this review failure was the reviewing firm's lack of qualification to do the work. Further, no specific guidelines call for nodes or construction stages to be included in independent bridge design reviews. The NTSB recommends changes to bridge design review procedures to ensure that bridge nodes and construction stages are included in independent design reviews. There should have been a proper review of the design, but there wasn't. Firstly, because of time and budget restraints, which I would say is typical. No engineering firm wants to give a big hefty fee to a competitor to check their designs. There is a bravado in engineering, a certain confidence in one's own ability to design an adequate structure, and nobody really wants to specifically commission another company to tell them otherwise. But there is a second part to this bullet point that is a bit more subtle. Further, no specific guidelines call for nodes or construction stages to be included in independent bridge design reviews. The NTSB recommends changes to bridge design review procedures to ensure that bridge nodes and construction stages are included in independent design reviews. Now, I can't be sure, but I suspect that this is a direct result of the choice to use reinforced concrete. In a regular steel box bridge, the nodes are a much less consequential part of the design. The weights are a lot less significant because it is steel and not concrete, so the loads are a lot more manageable. They generally have more than one truss, so overall each truss is doing half the job that the single truss is doing in this design. It might just be the case that the existing codes were not written to allow for the possibility of reinforced concrete to be used for a truss bridge, and that this statement that the review procedures need to be updated is a reflection of that. They need to be updated to include reinforced concrete truss bridges, literally because no one had thought of doing it before. For me, it just indicates how far out of the comfort zone the engineers were. There wasn't even direct guidance available for what they were doing. And this might seem like I'm postulating to quite a large degree here. There's a lot of guesswork going on, but I have the benefit of knowing what's coming. This is not the only clue that leads me in this direction. Shortcomings in oversight of evaluation of and response to significant observed bridge structure distress prior to collapse. section 2.6. As soon as the bridge had to support its own weight, cracks appeared at the under-design nodes, particularly node 1112. Over the next 19 days, the cracks grew until the bridge collapsed. The construction and inspection firms working on the bridge were aware of the cracks and had reported the cracks to the design firm asking for guidance. The engineer of record at the design firm repeatedly indicated that the cracks were of no safety concern. On the day of the collapse, the firms met to discuss a plan by the engineer of record to remediate the cracks. The bridge collapsed as the firms were implementing the remediation plan. In addition, the repair work was conducted without closing the road below the bridge to traffic. The NTSB recommends changes to Florida bridge construction oversight procedures to emphasize the need for bridge and road closures to protect public safety when structural cracking, beyond what sound engineering judgment considers acceptable, occurs, and to increase state oversight of complex bridge construction. Okay, so steel structures don't crack. They yield and deflect. So the fact there wasn't any direct guidance available for what to do with the road as a result of cracking in a bridge is only relevant if the bridge is made of concrete or masonry, but Americans don't build with masonry. So this points me again in the direction of there was no direct guidance for what to do with a reinforced concrete truss bridge over a main road. The engineers were flying blind to some degree. Lack of redundancy guidelines in specifications for pedestrian and concrete truss bridges. Section 2.7. The design of the pedestrian bridge did not include redundancy in the bridge load path. As a result, when the 1112 nodal region failed, the bridge collapsed. The design firm incorrectly believed that the bridge had a redundant design. For typical bridge designs, a bridge designer would use a safety factor greater than 1 to ensure that the bridge was over-designed to prevent a collapse. The NTSB, recognizing that no design guidance exists discussing redundancy in concrete truss bridges, recommends that bridge design guides include a discussion of redundancy in concrete bridge designs. Redundancy is a really important concept in bridge engineering. I'll get to technical details later. And this bridge did not have any of it. But once again, it would seem that there was no actual guidance available for what level of redundancy should be specified for a concrete truss bridge. The guidance, by implication, would only seem to be relevant for steel truss bridges. The engineers were flying blind. They were doing something that hadn't really been done before, and the guidance they would otherwise rely on did not exist for the specific thing they were trying to do. But instead of using the existing regulations to deduce a general philosophy for what should be done, it feels to me like they instead used it as a series of loopholes the way a lawyer would. Almost like, this guidance doesn't apply to us, no guidance applies to us, I guess we can do whatever the hell we want. It feels like instead of approaching the guidance the way an engineer should, as a guiding set of principles, and that there's an ultimate limit to what can and can't be done, they approached it instead the way a lawyer would, trying to find gaps and loopholes that they could work around. It all just feels wrong. And I'm not blaming the guidance here at all. Revolutionary concepts come along all the time and they need to be tried out. But the engineers trying that shit out need to be 100% certain, with safety factors, that they don't cross that ultimate limit. Instead, it feels like they exploited the guidance that was available to excuse their poor designs. I don't like it. I don't like much of this, to be honest. Anyway, from here, the report gets a little haphazard, bringing up topics in some sections and then dropping them, only to bring them up later. It is conforming to the structure of a report, not the structure of a story, so for the rest I'm going to try and break it down into sections that will hopefully tell that story a little bit better. Main structure. This is the proposed final image of the bridge, which it obviously wasn't able to achieve because it collapsed before it could get here. And apologies for the quality, I'm working with a government document after all. From an outside observer's point of view, this doesn't actually look like a concrete truss bridge. Well, okay, it obviously has the truss part, but from the outside this looks like a cabled stayed bridge. Like this. Or like this. Or like this. But for the bridge we are discussing in this video, the things noted as steel pipes and upper pylon are not structural. These are architectural gimmicks to make the bridge look like it is a cable stay bridge. The main structure of the bridge is the truss. Everything else is window dressing. The next thing to note is that the configuration of the truss, principally the angles of all the truss elements, these are all oriented to line up with the geometry of the completely useless pylon and steel pipes. The precise angles and lengths that form the zig and the zag along the middle is not determined by any engineering principle, it is solely at the service of the architecture. Or do I not like this? I have a whole pet peeve about architects messing around with the engineering of bridge designs. Dear architects, look at the way Norman Foster designs bridges and take note. Kind regards, Bigfoot. From an engineering perspective, all these changes in angles, the irregular geometry, it makes the bridge a complete nightmare to design. We generally look for repeatable junctions so that we can take a worst case and design a single connection, but with this bridge, every connection is bespoke. We aren't at liberty to alter the geometry to increase strength at certain critical points in the bridge. We can't add more truss members without adding more pointless steel pipes, and adding more pointless steel pipes will alter the geometry of the truss in ways we can't control. We aren't able to design an engineering work of art because it is being held hostage in order to be an architectural work of art, and that architectural work of art has problems. A brief foray into structural design. I'm just going to read a brief extract from the accident report. Structural design typically follows a two-step process in which the designer first analyzes the structure to determine the forces, demands, on the structure's components due to the applied loading, and then designs these components and their connections with sufficient capacity to withstand those forces and demands. The designer uses provisions from the applicable code or specification to ensure that each structural component and connection has enough capacity to withstand the applied demand. The language being used here is a little foreign because I'm British and our systems are a little different, but the principle remains the same. First, we do analysis. For a bridge like this one, I would imagine, hope, it was analysed on a computer. So we build a virtual model of the bridge on a computer, we apply all the loads to it that we think the bridge is going to experience, and then we click on Analyze. This will give us all the forces on all the elements in the structure. This is what the report refers to as demand. Once we have the demand, we then have to select a structural member that is able to withstand the forces that have come out of the computer and that the member needs to resist. A member with sufficient capacity. The capacity of a member must be greater than the structural demand. But it can't just be greater, it needs to be a prescribed percentage greater, and depending on the situation, that percentage might be greater than others. This is the factor of safety. The gap between the demand on a structural member and the capacity of the structural member. Increase that gap and we increase the factor of safety. In the UK, the capacity of a member is the capacity of the member, and then we use safety factors on our loads to achieve the factor of safety. It would appear that in America, both values, the capacity and the demand, are varied with factors to achieve the same overall function. It's not important. We have the demands on a structure, we have the capacity of the structure, and the difference between those two numbers is what represents the factor of safety. We can make a structure safer and less likely to fail if we use a higher factor of safety and increase that gap, which is kind of obvious when you think about it. The engineers who designed the bridge made 4 computer models of the bridge, each to represent a different stage of the process. Stage 1 was casting and fabrication on the side of the road. The structure is essentially continuously supported in this configuration, so structurally it was basically doing nothing. It's just a monument at this point. The rest of the stages are displayed in this figure. I'm going to refer directly to the report here. FIG used 4 analytical models for the superstructure final design calculations. The models were used to evaluate 3 critical construction operations. Main span transport during stage 2, main span in simply supported condition with members 2 and 11 both tensioned and detensioned at the conclusion of stage 2, and the completed bridge at the conclusion of stage 4. All of this is good until we reach this paragraph in the accident report. Designers of a complex and unique bridge should always document design approach, analysis, methodology, and key assumptions for all critical construction stages. However, the level of detail included in the FIG bridge design varied for each construction stage, with the fully completed two-span superstructure having the most thorough documentation and the simply supported condition, its state of collapse, having the least detail. So it would appear that, although all of the correct construction sequences were considered, the relevant model for the stage of when it actually collapsed has a low amount of detail. That is not suspicious at all. I mean, if I had designed a bridge that had collapsed, it is possible I wouldn't want anyone seeing my computer models either. Regardless, the source of the errors could not be identified because the model didn't exist, and so the investigators had to do their own analysis and make their own computer model. It's just incredible. Redundancy. 1.3.3 Redundancy Requirements. A typical truss bridge design includes two parallel trusses that are connected with lateral supports and bracing. Although there is a wide range of variability in truss bridge design, trusses are often constructed using evenly spaced and similarly shaped triangular sections running along each side of the bridge. The FIU pedestrian bridge had a single truss constructed of asymmetrical triangular supports running down the centre. Concrete truss bridges are rare. NTSB research found no other designs similar to the pedestrian bridge. Although truss bridges can be made from a variety of construction materials, they are typically constructed of steel because of the inherent need for trusses to carry both compressive and tensile forces. If we look at the typical box girder bridge from before, if any one of the structural members suddenly decided to fail, then the bridge wouldn't immediately collapse. It might collapse in a set period of time, but in the immediate future, it would probably stay upright. This time delay allows people to prepare for its potential collapse, to stop driving on the road or to stop sailing underneath it. At an extreme extent, it might even allow enough time for the failed part to be repaired or replaced and to remove collapse from the equation altogether. In terms of numbers, the actual level of redundancy is difficult to define. This box bridge has a redundant design. The FIU bridge with a single truss down the middle, this was definitely not a redundant design. The failure of a single member is likely to mean instant and total collapse, as could be observed by what actually happened. But equally, if we added more members to the box bridge, then we would make that bridge more redundant. None of these things can be mathematically defined, it's more of a general argument. But the engineers of the Florida International University Bridge classified their concrete single truss bridge design as redundant. As a result, they were able to use lesser factors of safety than they would otherwise have been able to on a bridge that was essentially completely new structural engineering technology. They did not play it safe. They were pushing things to the limits of what they could justify. There was no redundancy in the bridge design, and they should have been. Lives would have been saved. By the letter of the law, it would appear that the guidelines did not specifically require redundancy in a concrete truss bridge, but only because of omission and not because of any clauses that specifically prescribed it. The precise mechanism of the bridge collapse, a single point of failure leading to instantaneous collapse and catastrophe, this would not have happened if the bridge had been designed with a higher level of redundancy. Casting procedure, shear, and a whole load of other technical stuff. 1.6.2.1 Process descriptions. False work, cold joint, interface shear. The pedestrian bridge superstructure casting sequence included 3 distinct pours of concrete, with the bridge deck cast first, the truss members cast second, and the structure canopy cast last. Concrete was mixed and placed in a semi-liquid state into pre-constructed formwork, which was designed to hold the concrete in a desired shape while supporting the material's self-weight. Each concrete pour was to be completed sequentially, with significant time allotted between pours to allow for development of the concrete's mechanical properties. False work was used to support the formwork and the poured structure. The process we are describing here is the one by which the concrete is being cast. It is not possible to cast the whole bridge in one go, so they cast it in 3 stages. Stage 1, they cast the main deck, then they let that go off. Then they do the diagonal zigs and zags and let those go off, and then they do the canopy and let that go off. This creates a situation where there is a natural break in the material of the structure at these cold joint locations. This diagram on the screen, this is node 1112. This is exactly where the bridge went wrong, by the way. This image displays a few structural elements. First we have the deck. This element will be taking tension. The tension will be greatest at the centre of the bridge, or at least it would be if it wasn't being post-tension within an inch of its life to remove that tension. At the top we have the canopy. This element will be taking compression. The compression will be greatest at the centre of the bridge. The compression in the canopy is increased dramatically over and above what it would experience under just the ordinary bending loads as a result of the post-tensioning required to keep the deck from developing tension. The diagonal chords, the zigzaggy bits, these are essentially taking the bridge shear, and as such the maximum forces in them will be at the supports. Depending on the orientation of the chords, they will be taking compression or tension as a manifestation of that shear, in the same way that the deck and the canopy are taking compression and tension as a manifestation of the bending loads. Because of the way member 11 is orientated, it will be taking compression. If it was orientated like this, then it would be taking tension. The angle of the chord will determine how much force that member is taking. If we alter the angle so it was like this, then it would be taking less compressive load. This is important for members in compression because the longer a member is, the more likely it is to buckle. So by making the angle of this chord shallow in this manner, it is both increasing the load that is on it and decreasing its capacity. It's a double whammy, and both whammies are bad. So member 11 is in compression and it is at a shallow angle. I'm going to use this piece of wood to illustrate my point here. In a vertical position, when I apply load to the piece of wood, the bearing surface will return a vertical force back and the system will be stable. If I tilt the wood a little bit and apply a vertical force, then as long as I don't exceed the friction between it and the table, then it will be stable. If I increase the angle even greater, then when I apply a force to the piece of wood, it will slip away. The greater the angle of the member, the more horizontal force is required to restrain it. And this chord is acting the exact same way. It is pushing all this load onto this cold joint at an incredibly shallow angle. The horizontal shear caused as a result of this is magnified because of the angle of the chord and the level of force in it. It's actually a triple whammy. And to top it all off, there is a natural break here caused as a result of the way the concrete was poured. That because of the casting of this joint, it was already weaker to shear than a proper piece of cast concrete should be. It didn't help that the preparation of these cold joints was poor as well. The report mentions a couple of times that these cold joints were constructed incorrectly. This junction is incredibly highly stressed. It was constructed badly and it was taking about twice the amount of load the engineers thought it was. It really is no surprise that this is where it went wrong. A little later in the report we have this image, which shows all the rebar in the location of the node that failed, and there is a lot of it. Member 12, the vertical member, looks about proportionate. The diagonal member, 11, however, there is a lot going on in there. Remember when I said there was a delicate balance to be had with the amount of rebar in a concrete section? Well, this feels like too much to me. But it is possible I'm reading too much into a single, potentially exaggerated image. The final nail in the coffin. Up until this point, I spent a lot of time talking about problems. Maybe problems is the wrong word, and maybe challenges is the better one. Because although all of the stuff I've discussed so far is problematic, challenge-o-matic, none of it should have been a showstopper. If the bridge was designed correctly, then those challenges would have been successfully overcome, and we will be talking about how the engineers succeeded in doing something incredibly difficult. Something which, through all approximate rules of thumb, the kinds of things I've been discussing up until now, was inherently not suited to the job being asked of it. The reason why all of this is relevant at all is because the bridge failed, and those inherent weaknesses now no longer look like challenges, but issues the engineers failed to address. They now look like problems in retrospect because the models that were used to analyse the structure were not used correctly. This is where we directly address the mathematical error that led to the collapse. This is what I believe to be the fundamental miscalculation. We start here, back in the accident report. Post-collapse, the FHWA identified two consistent errors by FIG in its interface shear computations for the bridge design. The AASHTO LRFD article 5.8.4.1 states that the value for PC used in the capacity calculation must consider only permanent net compressive force normal to the shear plane. The FIG design value of PC considered the compressive forces from both permanent, such as the dead load of the structure, and non-permanent or transient loadings, such as pedestrian live load. The immediate consequences of this statement might not be obvious, but in my opinion, this one single paragraph describes the actual critical error that led to the collapse of the bridge. Remember, during the executive summary, we read that the bridge was essentially taking double the amount of load that it should have been. Well, this is where I believe that error originated. But to explain it in a way that is understandable to a non-structural engineer, we're going to need to take a hike. The main loads on a structure are as follows. Dead loads. These are the loads associated with the self-weight of the structure itself. The floors, walls, roof, everything that the building is made of is called a dead load. These are permanent loads that the structure has to bear every day that it exists. Live loads. These are the loads associated with the use of the structure. If it's a school, then it's people and desks and books and such. If it's a parking garage, then the live load is the vehicles. These are variable loads. At any one time they could be zero, but they could equally be at the maximum allowed. These are the main loads, and they principally act downwards vertically, in line with gravity. And for most structures, this is the dominant situation. Dead loads plus live loads putting our structure under vertically downwards actions in a detrimental fashion. But what if loads caused a beneficial reaction? When we design a structure, we are looking for the worst case, and that is generally dead load plus live load, but sometimes more load on a structure makes the situation better. So the worst case could potentially be just the dead load on its own. It is easy to imagine our jobs as structural engineers as one which is primarily about identifying the worst case and then designing the whole structure for that situation, but it is actually about identifying a load envelope. We need to be able to imagine a structure when it is being loaded to its maximum, as well as with how it is loaded at its minimum. The envelope being the gap between that maximum and that minimum. And in some situations, it is the minimum loading part of the envelope that is dominant. Let's take a steel building. In the UK, we would need to design all roofs for snow load. That is the maximum vertical downwards loading that a roof will experience. But when a big gust of wind blows against the side of a steel building, which is inherently weightless, we aren't able to include the snow load, which would hold the building down and help prevent the building from blowing away, because there's no guarantee the wind would be so polite as to only blow hard when it has recently snowed. The snow load on the roof, which is the variable live load, needs to be assumed to be zero for the wind loading scenario, because that snow is beneficial to the loading system as a whole in that scenario. For the maximum wind loading scenario, all live loads are assumed to be zero because they would all be beneficial to the structure in some way. For the maximum wind load scenario, we only include the dead weight when we calculate whether the building is going to blow away or not. Some load types are beneficial to a structure, and when that happens, the critical combination we need to check is when only the dead loads are being applied to it, when the structure is completely empty. At node junction 1112 of the Florida International University Bridge, this is the critical miscalculation that caused the collapse. For this junction, the one that failed, the scenario when member 11 was loaded with the maximum amount of load, this created a more beneficial loading scenario than when only the dead load was being applied. The more force that was being applied at this junction, the less work the junction was effectively doing because that force was clamping the structure together. The most detrimental situation that this junction would experience was when this clamping force was at its minimum, i.e. when there was no live load on the bridge, and the engineers did not consider this scenario. They did not appreciate that they were only exploring one edge of the envelope and that the other edge, the one that they were ignoring, would eventually lead to disaster.